Welcome everybody to this Talk Aeros event. We've got the pleasure to welcome Sinjin Youngman, who's going to talk about this fabulous aeroplane on our screens and give us all the gen. Sinjin's an aerobatic pilot, so you know, knows the right way to fly aeroplanes, and I'd be fascinated to learn how he thinks electric power is going to influence our sport ultimately. May I ask everybody to put their microphones on mute, please, while Sinjin's talking. Not least, it makes the video recording better because we get to see Sinjin while he's talking rather than whoever's making a noise in the background. Thank you very much, and over to you.
Yeah, thanks, Dave. So, so my name's Sinjin Youngman. I'm Electroflight's managing director. So today we'll this presentation I've had for a while, and I actually developed it for a conference, and it effectively runs through the ACCEL E-NXT program and mainly the propulsion system. And on the end of it, I've bolted on, well, how does this affect our world of aerobatics, and how does this disruptive technology that we've developed, how do I think that's going to come and see its way onto an aerobatic airplane in the future? It's on auto slide, so I'll have to keep going back a few times. So a little bit more about me. Growing up, big passion around engineering and aviation. Pursued the aviation side of things to try and get into the Air Force, which I was successful, and then immediately made redundant in that weird world of defence reviews a little while ago now. And then that forced me to reconsider my options and go, well, what else am I interested in? And engineering was that topic for me fundamentally. I was very fortunate to, through flying connections, get linked with an automotive engineering company that at the time were doing in-wheel electric motors. And from a very young age, I was basically surrounded by this early days electrification of automotive. Now, this was, although not that long ago, it goes to show how quickly automotive has moved on. This was pre-Tesla, and we were building high-performance EVs from the ground up, building battery systems, integrating our motors to demonstrate that company's product. So from there, I was very lucky. I was learning from an amazing team of people. We were really on the forefront of that sort of technology curve. What I was learning, you couldn't learn at university, so at that time. So I was really fortunate, and then that gave me a great background to go in and have a relatively short career in automotive electrification and motorsport. I worked a bit of time at McLaren Automotive before going to Jaguar Land Rover, back to the startup company where I went out and worked in China for a couple of years, and then I was very fortunate, met Roger Target, which some of you may know, and Roger was Electriflight's founder, who'd been pushing this concept of electric aircraft for a little while, and I had a fantastic website, and when I got in contact with him, expecting if I was lucky I'd be able to turn up and help maybe polish the aeroplane or something like that, and actually speaking to Roger, became really aware that yes, he'd got this fantastic airframe concept, but the propulsion system was yet to be designed and detailed. And then that's where it became obvious that my knowledge and skill set from automotive, coupled with, at the time, and my passion for aviation and aerobatics and high performance airplanes, was a perfect opportunity to sort of combine those two passions for me. And that's when I started getting heavily involved with in Electroflight, joined Roger as sort of pretty much employee number one. And that's when we met Rolls-Royce and struck up a relationship with Rolls-Royce. And at the time, I was fresh from, I'd been to Reno for the first time. And at Reno, you see some pretty amazing things from an aviation perspective, whether it's sort of 2,000 horsepower unlimited, but also the sport class was pretty amazing what people were achieving with a standard or sort of a light sport airframe. And the NXT was one of these airframes that stood out to me. And at the time, being sort of engineering dreamer like some of us are, where you sort of design concepts and just do sort of hypotheticals, I actually did a hypothetical analysis on could you do an electric NXT, and at the time that sketchbook drawing I didn't think would ever come to fruition, because being in engineering, I knew how expensive engineering was. And obviously, when we got together with Rolls-Royce and we started throwing around ideas of projects that we could get together and run, I pushed forward this project idea, thinking it would be immediately rejected, and actually it gained a lot of traction. And so moving on to the slide here, I mean, so what is ACCEL all about? So it's very hard to go and get funding just to go and break an airspeed record. You've got to link some industry level relevance to it, and that's what this program does. So it's all about flight demonstration fundamentally. So Rolls-Royce to date haven't flown an electric aeroplane. For them as a powertrain company, it's really important that they build a flight demo in an affordable way, and this program has allowed them to do that. In terms of power as well. So the great thing about going and setting a record, the requirement in terms of power was, well, basically how much power can we get in it, because that's going to always help speed record. So that pushed them from electric aviation maybe 5 years ago, where there were a few aircraft flying with maybe 100, 150 kilowatts, and actually we wanted to push that a fair bit further forward. So we're up at 400 kilowatts on this on this program. And the other, just to mention the other partners on the program, so it's fundamentally an Aerospace Technology Institute sort of match funded program. So that's the aerospace's branch of government funding that looks at great R&D programs and says that let's support that program. So we're very fortunate to have half the program cost covered from them, and also YASA Motors. So YASA are sort of a British automotive startup company spun out of Oxford. They've got some fantastic motor technology. They've very recently been acquired by Mercedes-Benz, which is really exciting. And they've actually spun out part of the company to go serve the aerospace market. And actually that happened because of this program. So it goes to show there's some great elements there. In the bottom right, you'll see my outdated presentation of airspeed record in the spring/summer 2021. Didn't come to fruition, as most of you guys know that have done anything with aviation and aeroplanes. It always takes longer than you think it will, and there's some complexities there. But we're well on the way now, and we're flying, and we'll talk about that in a minute. So moving on to the propulsion system a bit more. So here is the propulsion system out of the aircraft in this picture here. It's fundamentally 3 YASA 750R motors all stacked together onto a single shaft. So this is a standard, effectively a Lycoming propeller flange at the front. So we use an MT electrically adjusted propeller, and then everything from the back of it is slightly different. So you have a single shaft that runs and connects all 3 of these motors up. So that's quite an interesting concept, because fundamentally each motor is driven by its own inverter, and then it has its own individual battery system. So we actually have triple redundancy through the whole powertrain up to the mechanical shaft that links the propulsion systems together. So although not, obviously we've only got a single propeller, so we're not saying we're fully redundant, but that's a very high integrity, high reliability part. And actually in all of the experimental elements of the project, so that for instance the battery, the motors and the inverter, we were actually redundant, and that was quite an interesting concept. And although it doesn't help us go faster, it's an industry relevant concept to push through. We've also followed that through into the cooling system. So the cooling system is decoupled, so each motor and inverter and battery are cooled in a different way, so that we don't have any common cause or common mode failures there. One thing that you'll notice that's quite interesting about the aeroplane, so it's a 400 kilowatt, which is 530 horsepower roughly, aeroplane, and the entire propulsion system is cooled by these 2 relatively small Naka inlets here, which obviously compared to a standard sort of set of Lycoming sort of cheek inlets for the cooling there, what that demonstrates is effectively the thermal efficiency benefit that you get with an electric powertrain. So this entire electric powertrain operates at about 90% efficiency. So 90% of the electrical energy in the battery gets turned into mechanical energy at the shaft there, which compared to a Lycoming, which I don't think anyone's actually worked it out, but it would be very horrendous, down at maybe 20%. For for contrast, that about the maximum efficiency you can achieve from internal combustion engine is about 50%, and the Formula One guys have done that with these amazing V6 hybrid turbos at the moment. So 50% of the fuel energy has been turned into propulsion there, and they're doing that through these super complex hybrid turbo type arrangements. So they're recovering a lot of energy there. So you can see that 90% is one of the big advantages that you have around electrification. So when you're doing the trade-off and people are saying, well, how much energy is in fuel versus how much energy in battery? Well, something that people forget to mitigate is actually the battery energy is used a lot more efficiently. Admittedly, not enough to get anywhere near to the fuel energy density, but it starts to make a difference. So we've spoken about batteries a fair bit already, and the battery fundamentally is the heart of the aeroplane. It's the biggest, most complex element, and it's the biggest part of the program for us from a development point of view. This is where we spend a huge amount of time and effort. So you can't go and buy the battery system that we wanted off the shelf. We wanted to develop that. Electroflight as a business, our core business now is around that battery system. That's where today there's the biggest opportunities in industry, and that's why we're going ahead, and we now design and build battery systems for a number of customers in the aerospace electrification market. So you can see here in the picture, you've got what we call channels. So each battery, each channel, so a sort of a line of battery here, is actually made up of 6 individual battery modules. And each of those 6 equates to a 750-volt battery system. All 3 of them, when the lid is on, are actually isolated from each other. So there's no electrical, mechanical, or environmental interface between them. And we do that, again, to try and drive this redundancy back into the system. So if we were to have a thermal runaway in one of the cells that propagates through the pack, we can actually shut down that battery system and continue to operate on the other 2 battery systems. So that was a key sort of concept that we developed. The battery system's built out of 6,480 18650 cells. So these are a type of cylindrical battery cell, lithium ion, that the automotive industry heavily use. So Tesla pushed ahead, and they still to date use exclusively cylindrical cells. The cells that they're using are getting slightly bigger. So the 18650 actually describes the format of the cell in terms of millimeters. So it's its height and width. So for instance, we now use cells that are 21700, so they're a taller, fatter cell in comparison. But for the record profile that we have to find a balance. So with cell chemistry, you're balancing energy versus power. So we could have fit a lot more energy into the aircraft, but we'd have not been able to discharge enough power effectively to go set a speed record. So that's the trade-off that you're constantly managing. For an airspeed record, obviously our focus is going as fast as possible and only having enough energy to achieve that airspeed record. So that's why we've got a relatively low 72 kilowatt hours of total energy. But what's different about this battery is that it can deliver 400 kilowatts of continuous power. Now, all of these electric cars today, and this is one thing that is really important to take away, is electric vehicle duty cycles are quite different. So Dave mentioned you've got your nice new Jaguar, and yes, the performance is fantastic, but you use the performance in a very different way. The demand is very transient. So if you put your foot down and do a 0 to 60 run, or even a 0 to 100 run, if you're feeling brave with your license, that's still only taking 5, 6, maybe 7 seconds at full power. As you know, aerospace is an entirely different environment where you need a very continuous demand, and often that demand is very, very high, and that's exceptionally challenging for battery systems. So this battery here can do 400 kilowatts continuously. It could also do a megawatt peak. So if you put this into a car, you could go produce crazy horsepower like some of these crazy supercars do. So over 1,000 horsepower peak is absolutely no problem, but 400 kilowatts continuously is actually really challenging from a thermal and an energy point of view. So some other interesting features about this battery system design is that the case itself, so the case that the battery sits in, is a structural element. So you'll see in a minute, actually, if we go back, the propulsion system mounted onto the front here So we've got very standard AV mounting system. The loads from this propulsion system go into the battery case, and they're resolved at the airframe a bit further back, and we'll have another look at that later. So we did that to try and get some better aircraft sort of system efficiency. Some other points to note: so this is a 750 volt battery system, so it's what would be considered of higher voltage. So traditionally at the moment, most electric cars are at about 400 volts. One of the ways that they're going to start pushing the charge rates and making charging systems faster is by increasing the voltage. So Porsche and a few other of the bigger car companies are pushing higher voltage systems now, and we did it for the same reason. It means we can charge the system faster. And if you sort of go back to sort of basic electronics lessons, so V equals IR. So if you can increase the voltage, you can reduce the current for a given power. And that's effectively what we have to achieve. Otherwise, you end up having so much current going through your metallic sort of conductors that you produce a lot of waste heat, and that's really bad. So if you can push the voltage as high as possible, that's really advantageous. Here you go. Here's just another view of what that battery system looks like. The packaging is super integrated. I mean, we've got a really great design team, really experienced design guys, a lot of them from automotive and motorsport. So it's all about the detail of the design. It's it's very compact, and you sort of get that sort of beautiful elegance that you see with some engineering. And so we're really proud to sort of show what's underneath the battery here. What's also interesting is it's a liquid cooled battery. So we've got 750 volts, and we're flowing highly conductive fluid through it, which is a bit counterintuitive from the safety perspective, but you really must do that to get the heat out of the battery. Otherwise, you'll be in a situation where you overheat the cell before you've got all of the energy out, and that's really important in any high power application. The thermal management of the battery is really quite critical. Here in the top left, we can see that propulsion system on its build frame there. What's quite interesting is where the challenges lie around electrification in aerospace. So you can see the NXT in the background. Now, when we build the aircraft and put the two together, we actually push the aeroplane onto the battery, because the battery and its propulsion system is about 700 kilograms, and the airframe itself, a beautiful, lightweight, fully carbon fiber airframe, is only about 300 kilograms. So it makes much more sense to just push the aeroplane onto the powertrain. The powertrain itself in this sort of sat here on the build frame, it can actually operate entirely separately from the airplane. So we could power it up and spin the shaft with it all sat here. And we did that because we wanted to keep the airplane as simple as possible. You can see here on the right, this is the composite structural battery case that we mentioned. So yeah, really key element of the design. Obviously, as you can imagine, there's a lot of design analysis that goes into the background here. And that's what's, these programs, that's why it takes 3 years to sort of design, build, test, validate this. And obviously, we were building an aircraft for Rolls-Royce. Rolls-Royce are a major FTSE 100 company. They have a huge reputational damage potential, and that's why even for a demo aircraft program like this, the level of engineering we went to is extremely high. And that's what people forget often when you compare to a pure startup company building an aircraft, that you can take a different level of risk. So effectively, this aircraft's been held to very, very high design standards. In some areas, it's actually up to a certification standard. So that was a big challenge of the program in terms of time. So thermal runaways. So this is a big topic of the day, and specifically in aerospace, where you're effectively in the air, you're with your battery system. If you have any kind of thermal event, your ability to get the aircraft on the ground and get out isn't the same as it is in automotive. So our approach to this is quite different. In automotive, the safety case is well known now. Yes, there are some issues in thermal runaways. If you put Tesla fire into Google, there's lots of examples in early days of fires, and fundamentally, if you build enough vehicles, they will happen. But in all of these cases, the passengers are able to get out pretty much every time. Aerospace is slightly different. We have to design to contain the fire for as long as possible. So we've got sort of a rigorous design kind of methodology that we have to try and prevent it, to try and reduce the probability of cell fires, and you do that through not abusing it, so controlling it. That thermal management I spoke about earlier is really important. So you've got to look after the cell as best as you can, and then if and remember, aerospace is all about, you build lots of mitigation in, and then you pretend none of that mitigation works, and you still have to go to the next level of engineering to stop the next problem that happens. And that's the challenge of aerospace in this century, is that the level of safety of the products today needs to be as good as the outgoing technology. Whereas obviously we all know back in the pioneering days of the piston and jet age, safety levels were shocking compared to where they are today. So these are the challenges we have. So we've got to solve all of these fundamental safety problems before we go to market, not develop it through over time. So that's just, yeah, an interesting factor we have to deal with. So picture bottom left is actually a single cell going into thermal runaway. It's pretty ferocious under certain conditions, and that's the challenge. So remember, 6,480 of those cells are inside our battery case. So there's a lot of flammability, and it's not just flammability. It's actually, they're almost like fireworks. There's a force behind that reaction. So on this program, we actually designed some sub-module testing so that we could actually build a representative case, and we could see how well our protection systems work at containing that cell fire, and we force a cell to go into thermal runaway. And we're pleased that we met our objectives. So we basically have a 10-minute containment strategy. So a cell can go into thermal runaway, and we know that we have 10 minutes to get the aeroplane RTB'd back on the ground. And even then, we managed to actually demonstrate that we think we might be able to contain it indefinitely, which is good because you might be able to save the aircraft at least. But yeah, a lot of design effort goes into this stuff. You can see at the top right, that's the charred remains of one of the smaller modules. But actually, not all of the cells in this went off. So we managed to stop the fire from propagating all of the way, which is a really big win for the design. So maybe 20 cells went off in this event here. So yeah, we've mentioned about cooling. So one thing that we all love about existing air-cooled aircraft engines is that it's effectively the simplicity of the cooling is fantastic. It's effectively passive. There's no failure modes unless other than maybe blocking an intake or something like that, and that's actually really good because simplicity is just lightness, and that's how the aircraft that we have today, aerobatic aircraft of great performance, is effectively they're very low on system complexity. The challenge that we have going forwards into electrification is as you push power up, the system becomes a bit more complex to deal with that. So the cooling system within the battery is one of those examples, and obviously that has that cooling system has to reject heat into an external radiator of some sort, which we'll show you in a bit. The other thing we do is we actually do pre and post flight conditioning. So to get the most out of the battery system, so battery cells have their internal resistance varies with temperature. Now, this is why when on most modern electric cars, they have preconditioning cycles, so that when you get in the car, it's preconditioned the cell to the perfect temperature that will give you the maximum range. And it's also why that if you get into your car in the winter, fundamentally the lower cell temperature has increased its resistance, therefore you'll get less range. So we combat that by pre-selecting the temperature that we want the cell to be at, so that we can make sure we've got the cell in its most efficient operating range for as long as possible. We also do it because cells can be discharged up to quite high temperatures, so all the way up to about 80 degrees C, which is pretty damn hot. But what they can't be is charged at that same high temperature. So you can regen only about 40 or 50 degrees C, which is why sometimes people in, again, electric vehicles will notice the regen isn't always consistent. So if you drive the vehicle very, very hard and heat the battery up, at a certain point, it will stop letting you regen back into the battery. Now, that's obviously a bit of a challenge in this aerobatics context, where you're going to be getting the battery very hot. what that means for us and the NXT is actually when we've got the aircraft back on the ground, before we can charge it, we actually have to chill the battery. You have to cool the battery down and then start putting charge into the system. And you can see this is actually the bottom of the battery. These are the cooling quick disconnections that we basically use to go in to attach to the bottom of the aircraft, and we can condition it with almost like an AC unit, and we can bring the cell temperatures down. Again, fair bit more complexity, but it's what we have to do. Otherwise, if you didn't have that ability to cool the battery on the ground, we'd be limited to maybe 1 flight a day. At the moment, we can achieve between 2 and 3 flights a day because we've got this ability to control the battery's temperature so actively. Again, we mentioned complexity. Unfortunately, batteries aren't entirely passive. Again, we mentioned about some of those safety elements there. So the battery management system, and you can see this again, I find this picture really good. It's another example of the sort of beautiful engineering integration where it sort of, you give them a free space and they'll somehow manage to completely fill it up with hardware and electronics. And these are basically the battery management systems for for each individual battery system. Remember, one thing to note is that battery is fundamentally always on. So there is no way of actually turning a cell off. They are always on, which gives you some challenge, because what this BMS has to do is provide the protection system and the contactors, so effectively the high current switch in, to ensure that the battery becomes on and off at the right times. One of the other elements is just fundamental, I haven't mentioned it so far, is just fundamental safety. There are not that many ways of killing yourself with an internal combustion engine vehicle immediately, even if you're really adamant that you want to when it's stationary. Unfortunately, electric vehicles are quite the opposite. So you have instantaneously lethal voltages within that system, and it's why if you ever have the chance to have a look at the bottom of an electric car, they're very hard to get into to work at. And there's a lot of, if you start pulling bits of panel off, the signs that tell you to stop get more and more alarming, and they use all sorts of tricks and you need specialist tooling to get into the batteries, because they just do not want people working on the vehicles, which obviously presents a challenge in the aerospace, where obviously owner operators are used to maintenance type operations, whereas obviously here within this high voltage environment there are some challenges there. How do we keep people safe? Because electricity is so unique in that that there are no warning signs. You make a mistake and the electrocution is instant. So there are some challenges there in terms of keeping everybody safe. So testing. So again, just in terms of getting building a powertrain and getting it integrated and flying it is one thing, but actually you've got to create a safety case to try and demonstrate why that aeroplane is safe to go into the air. And that actually is a lot of work that goes into iterative testing to go and demonstrate that we did sort of thermal shock testing. This picture in the bottom left is the whole battery module went in on a big vibration table, and it went and saw up to sort of 50G pulse input. So we had to make sure that when you're in the air, it doesn't vibrate to bits. So there's lots of testing standards. So it goes to show the rigor that we went to make sure that the system was going to be safe when we put it in an aeroplane and put it in the air. The other challenge is manufacturing. So these systems are quite complex to build. Putting 6,000 cells plus cells together requires a lot of repeatability. You need every single battery module to be the same. So even though we're only building enough batteries for one aircraft, you still have a manufacturing challenge in terms of getting repeatability there. So that's something to factor in. It's very hard to go and build your own battery, even if you have the cells available to you. It's very time consuming, it's very laborious. And if you don't have consistency, you will not get good pack performance. So on to how does, so obviously the NXT at the moment, we've just started flying it. We're really pleased with the performance of the aircraft so far. A couple of times we've forgotten it's an electric aeroplane because we thought we'd be dealing with monitoring temperatures and all of this stuff, but actually we've been dealing with normal aeroplane problems such as landing gear and flying characteristics and some of that stuff. And the only time that we talk about the propulsion system is when we're cooling off the state of charge as we're depleting the battery. So that's really positive. So and I think we've all been a little bit surprised that we were so focused. We've got lots of scenario planning about all sorts of different failures, and to date we haven't had it's been a bit like people's experience driving electric cars. It all becomes quite simple, which is great. That's a good testament to the technology, and that actually in terms of the pilot feedback is that it's a really simple powertrain to operate. It's a single lever operation. They've been surprised at the lack of feedback. So I think they're all surprised at how much noise and vibration is giving you feedback of what power setting you're at. Whereas I think Phil noted it almost feels like you're flying an exceptionally high performance glider. Which is really interesting. So we've got all of these sort of learnings that will come out of it. At the moment, we're opening up the envelope slowly. So building G, building speed, basically getting up to the point where we're ready to go and sort of start breaking some records. That's really exciting, how that's going. But from perspective of aerobatics, obviously, myself being aerobatic pilot and building my own aircraft, obviously I don't think there's anybody more motivated to try and go make electrification of aerobatics happen. So sort of the next sort of the remaining time is going to be sort of my thoughts, just sort of taking sort of I'm very fortunate to have a really good exposure to industry and to sort of go through where I think we're at and when I think it might happen. So on the screen at the moment are some examples of sort of pioneers in this area. So these are the guys that have actually gone and done some stuff, which I think is absolutely fantastic. So top left, we've got Extra, who did the 330 LE with Siemens. Interesting aeroplane, very, very large battery, potentially not as much of the thoroughness in design as we've just spoken through, I've sort of demonstrated recently, but actually this was quite a few years ago now. It was a good effort. The aircraft was quite heavy from what I understand, and actually I think it was in the normal category, so it was actually not, they had a pretty low G limit, and that limited what they could do with it from an aerobatics point of view. I don't think it's flying at the moment, but obviously they learned a lot from doing it. The Siemens Twister is really interesting, and I think actually demonstrates quite nicely some of the challenges. So the Twister is a great platform, and I think obviously Andy McKee's sort of single-handedly pushing the popularity of the Twister for aerobatics, but actually it's a great platform, and it's a very, very efficient aeroplane from an airframe perspective, which means it can do a lot with a very low power level. Now, when you start talking about all those challenges we spoke to about battery systems and all these other elements, being at that sort of around about 100 kilowatts or less is really quite beneficial, because it means you can then push your battery towards that energy. So remember I mentioned about that sort of trade-off between power and energy. The moment you can slide the scale over to energy, you suddenly end up with an aircraft that actually has some usable endurance. And that's why if you look at today in the light aircraft market, it's stuff like the Pipistrel Velus with its almost ultralight category aircraft that have the best performance, is because they're sipping away using maybe 20-30 kilowatts in the cruise, which is fantastic, and actually really starts to make the battery system make sense. So I think they've demonstrated really what can be done at the lower performance end of the market, but obviously we all know the limitations of that airframe in terms of the sort of categories that it could perform at. What I thought was super interesting is the Votech Evolaris, which I think is an evolution of a One design from an airframe perspective. I think there was a university, they started a project that looked really exciting, but I don't think they've got that flying yet. So they actually used a geared motor, which is quite interesting. So that you get some really good power density from using a geared motor opposed to direct drive. But yeah, hopefully we'll see that flying one day. What else I've mentioned? Yeah, so the efficiency of the Twister is actually, I think, really, really quite important. So in terms of, so what are the blockers? So let's be realistic about electrification of aerobatics. So, okay, so let's imagine we want to try and build something that can compete at the unlimited level. I think at the moment, based on the work that we've done, it's possible, but you're going to end up with an aircraft with almost no ferry flying capability. So you're going to end up with an extremely range limited aircraft. So it's got a single point of use. Effectively, it's designed to go do that aerobatic profile with a little bit of reserve. So most of what I'm sure you've had most of what we've done on the ACCEL program is pretty what you'd call high value engineering. It's not it's quite expensive. I think we're still a very cost effective program. I mean, you can go look it up, it's publicly available. It's about, I think we spent about £6.8 million over just over 3 years. And remember, that's everything. That's all of the time, the people, the hardware. So that's fundamentally cost effective and is only just a bit more than what sort of a single Rolls-Royce gas turbine costs. So from what we've achieved from an R&D's perspective, it's good, but I think we can all agree that sort of development budget is beyond most players in the GA market sort of today, especially at the light sport end. So that's a bit of a challenge at the moment. The low maturity of the technology and the low as in the low, how close it is to feasibility means that you've got to spend some money to get the performance to where it needs to be. And unfortunately, like, the low volumes don't help. So you can't amortize your costs over 100 airframes. I think it'd be pretty ambitious to work around that. I mean, we've got to recognise we're a niche sport with a niche application. So yeah, that commercial model is going to be challenging. Charge infrastructure is pretty interesting. So let's imagine that we go out there, build a single demo aircraft, turn up with the aircraft in the glider trailer, effectively rig it, get it going. Charging the aircraft off of a standard sort of rural airfield grid is going to be quite challenging. I think you're going to be limited to one flight a day, and obviously that's a long way to go and a lot of effort to do one flight a day, even on the weekends where the weather actually plays ball. So so you're going to have to think about a different way around that. So you're going to need some sort of fast charge system, and you're going to have to bring that with you. So an interesting concept would be, actually, if you're fortunate enough to have an electric vehicle with a sort of tow capacity, you could actually use the energy within that vehicle to fast charge the aircraft. So batteries charging batteries is really good because they're very good at that high power profile, and then the car can, or the energy bank can then trickle charge over the longer period that it's sat there plugged into the grid. So you'd have to think of a way around that challenge. That's probably how you'd do it. You'd have a load of batteries in your trailer, and then you do a fast charge that way. Again, it's not impossible. There are actually Pipistrel that offer these training aircraft actually have these similar concepts. These are all possible, but as you can imagine, it's more cost and barrier to entry, so it's worth mentioning. The other challenge is, okay, so again, it goes back to the beginning around safety. So we had to develop an aircraft that effectively was close to a certification standard. Now, safety, unfortunately, adds weight in aerospace, and I think today we're all very happy with the safety level of our aerobatic type aeroplanes. But actually, if you sort of scratch away a little bit, where you've got fuel tanks in the cockpit and all of these risks, they are fundamentally higher risk sort of vehicles. There's some risk associated with aerobatics as a sport. So what's quite challenging is designing for that in today's environment, which is quite rightly the world today there's a lot of safety culture in the world, and going out there, so for instance, designing a battery electric aircraft for aerobatics, you could strip a lot of weight out by taking out some of these safety features. So let's say all of this thermal runaway protection. If you said, well, if there's a thermal runaway, I'm just going to jump out. Okay, so if you take that as a use case, the same as if there was a fire in the cockpit, I think a lot of people would take that decision. Actually, there's a lot of weight to be saved there, but whether you could drive that forward as a product and bring that to market, you certainly wouldn't be able to certify it. So that's a challenge. So Extra wouldn't be able to take that on and bring a new product to market. You might be able to do it under a sort of an LAA scheme, but again, it goes back to that sort of commercial model. You're back into that realm of you can't achieve the volume to get it done. So that's some of the blockers that we have today in sort of today's modern world, is bringing dangerous products to market is quite challenging, even if people want to fly that dangerous product because it's fantastic fun, and they accept the risks. That's actually quite hard to do nowadays. So that being said, Electroflight, we've basically worked up a concept for an unlimited aerobatic aircraft. So in the background here's a rendering. It's not as nice as it's not a complete design, but it's effectively a good concept that gives us a good idea of the feasibility of the project. And actually, we're quite excited by the results. We think that there's a really viable concept there. So a few of the ingredients are sort of reusing that ACCEL module that we developed. So we've already spent lots of time and money qualifying that module. Let's reuse that. That saves a good amount of cost there. And basically building from what we learnt there. We're planning to use a Rolls-Royce electric motor and inverter pairing, so really high performance motor and inverter, peak power of about 260 kilowatts, 350 horsepower, so plenty of power. Power is not the problem. The challenge that you then have is around weight. So the Edge 540 max takeoff weight is about the weight of the entire ACCEL powertrain without an aeroplane attached to it. So that goes, so the NXT is at 1250 kilograms, our takeoff weight. So it's actually quite a heavy light aeroplane by some measure. So how do we get back down to within sort of the Edge's max aerobatic weight is a bit challenging. We think we will end up with around about 40 kilowatt hours of usable battery energy, which is enough to go do takeoff, climb, sequence, and return. Some energy management is going to be required, potentially, depending on the sequence, but that may actually add it's an interesting element maybe to aerobatics in the future. It's not going to be about leaving not thinking about that energy usage, which I'm sure nobody does today. Effectively, you're always assured of having enough energy. So that's an interesting element that may be introduced in these early sort of electric aerobatic aircraft that could come through. Is actually there's a talent and a skill in managing the energy, a bit like sort of gliding times aerobatics equals electric aerobatics maybe. So yeah, really interesting concepts, and actually we're looking for options sort of to take this forward and develop it and build it. If the lottery numbers came up for me on Saturday, this is where most or some of that money is going to be going, is into getting Electroflight to develop this and go fly this. I think there's a great opportunity to go build it as a demonstration platform to show. Not that there's as we've spoken about, the challenges around the commercials are very difficult at the moment, but it's about showing that the technology is there or thereabouts and sort of waiting for the future to come. So there's some interesting opportunities there. I think World Championship Air Race that Nick mentioned at the beginning, let's hope they have a good first year or two. They've definitely got electrification on their radar. We're in contact with them and keen to, at the right time, offer them a solution. Air racing is also a great use case for electrification, in that you can manage the energy problem. You've got a very known flight cycle, and you can get away with not needing to ferry the aeroplanes. So yeah, so definitely possible is kind of the summary from that bit there, but there are challenges around getting it to a position where we're all able to go and buy one. But sort of the last thought that I'll sort of end up on is kind of the wider electrification picture, and why actually there is some hope. There's some room for optimism. It's not all doom and gloom from my side. I think there's some really exciting things happening. So it's worth mentioning that if you look at GA aviation today, and especially aerobatics, it's all been effectively funded through a stream. So let's take the Lycoming engine. The Lycoming engine wasn't developed exclusively for GA. Fundamentally, it was an evolution of a design. So, and today we benefit from that sort of slow iterative investment in a market. So GA aviation happened first, and then aerobatics happened as a byproduct, because obviously the feasibility of these aircraft increased. And I think we actually need to go through that same phase at the moment to end up at the same place again. And we're starting to see that at the moment. So industry is really responding, especially post-COVID, to the need for electrification, not just because of the green incentive. I think the green incentive is a big part of it. Governments are going to push very hard to decarbonise aerospace, but also there are some genuine commercial benefits as well. So the eVTOL companies are kind of the biggest demonstration of that. So they all think that there's extra money to take out of people's pockets in changing the way transportation works, and let's see how they get on doing that. And okay, I think some of us will be quite skeptical about whether we'll be flying around in volocopters or in the future, but what's important is at the moment it's creating a funding stream. So there are billions of dollars going into the industry at the moment, which means that companies like Electrifly are all being paid to develop technology, paid to develop solutions that are going to enter the market. Some are going to fail, some are going to work, and some are then going to get better. And I think that iterative approach towards sort of, and unfortunately this isn't going to be an overly fast process, but it's going to be a decade or two. I think we're going to start to see the powertrains become commoditized, and then the costs come to a point where we can all start looking at those propulsion systems as viable alternatives to sort of the aircraft we have today. So I think industry will get there, and I think it will happen. But I think we all need to be a little bit more patient, wait for the money to come flowing into the top, filter down, and naturally, of course, there'll be some technological advancements on battery technology that just make it a bit more convenient and viable. Because yeah, it's the how it is today isn't going to be for everybody. But in the meantime, I hope that Electroflight get the opportunity to build the electric edge. I'd like to. I think going and demonstrating that will be a fantastic start, and I hope other people likewise that are in a privileged position to be able to fund and operate and get out there. I think that sort of the onus is on us to go sort of pave the way a bit, and then hopefully in the future we can share the technology with everybody else and get everybody else building electric aerobatic airplanes in the future. So yeah, that's pretty much sort of the end of the sort of rambled on for quite a long time there, but I appreciate there's probably a bit of time for questions at the end.
Superb, thanks. Really excellent. You didn't talk. I know it's one of those things that's always kind of on the horizon, but presumably new battery chemistry is one of those things that's is going to move change the weight problem.
It is, yeah. So we've got a bit of a challenge though. So unfortunately, making cells is exceptionally expensive. So the companies there, and there aren't that many of them doing it. It's a multi-billion-dollar industry, and when they taking a cell from the lab to production is insanely expensive. It really is. It's quite miraculous to look at how long it takes them to do that. So once they've got it in production, they want to keep it in production for a long time, because it takes them quite a while to actually get the investment back and then start making it profitable. So that process basically is throttling the advancements in cell technology. Yeah. The other challenge that we have is, unfortunately, electric cars now have got enough range. You can, they don't need to have. If you've got 700 miles of range in your electric car, you've got too much range and your car's too expensive. So unfortunately, the automotive guys are now no longer pushing as hard for energy density. What they're pushing for is take all of the nasty, hard to get at chemicals and rare earth elements out of them and make them cheaper. Whereas in aerospace, we need the opposite. We still need the supreme energy density. But the problem we have is we're not a big enough market to drive the investment as quickly. So this is something we're really struggling with at the moment. There are some better cells coming, and Electroflight, our job is to be a part of taking those cells at an experimental level and developing batteries around them and bringing them on. But unfortunately, the step changes are happening a little bit slower than we'd all like, and that's something that is slightly frustrating. But we just can't drive those factors too much. But who knows? Let's hope for a big step change, because I think that's going to be required. But and solid state cells are probably the next one that's coming. But it's going to take some time to commercialize it. That's all.
Adding sugar to lithium sulfur batteries seems to be a thing at the moment as well.
Yeah, again, there's some amazing stuff happening in labs, but it's just so hard to commercialize it and get it built and reliable and all that kind of stuff.
Yeah.
Any more questions?
Yes, apologies, I missed the beginning of the presentation. What battery chemistry are you using?
So it's an NCA, so nickel cobalt. I can't remember I should know that. I can't remember the last bit, but yeah, it's a stand. So it's a Murata 18650 cell. So it's made by what used to be Sony cells. It's called a VTC6. You'll probably find that if anyone's got a Bosch drill at home, you've got 4 of them in the battery pack there. It's actually, if you think about a drill or a Dyson vacuum cleaner, the duty cycle is pretty much the same as an electric aeroplane. You take it off charge, you run it flat out for 7 minutes, and you put it back on charge again. So actually, the duty cycle at a cell level is very similar. So yeah, so we're using a standard sort of automotive intent NCA lithium cell.
Have you looked at LMP?
Yes, yeah. Yeah, so LMP, we effectively we have a library of about 250, 300 cells, and we've got all our clever cell guys. Basically, every project we do, we've got this big process that we go through to try and select the best cell. Yeah, there's always a balance. So you can get some better energy density, but they often suffer on power. Life is a problem as well. That's also the problem with a lot of the sulfur type cells, is you only get maybe 100 cycles out of them at abusive demands. So there are some challenges pretty much everywhere. But
that's what the sugar does, apparently.
Changes the life, does it? Okay.
Yeah. So it gets you up to about 1200 charge cycles. So similar to regular cells, apparently.
The advantage of LMP, I've just done a project in Australia using LMP on buses, and you would not need a cooling system. The energy density is quite high. It's higher. It's probably higher than what you're using, and they're very, very light. But
they probably won't do 6C or 7C. That's going to be the challenge. They won't do the power density. I'll check, but I'm pretty certain they won't do. And obviously the benefit of obviously a bus pack, I assume you're pretty big. It's a very large battery, so your per cell loading becomes much lower, which often, I mean, and which might be an option if we were doing a very, very, very large pack, which we might do in the future. So obviously some of the big commercial applications might need very, very large packs, but yeah, at the smaller end, I think you might suffer with the power density. But again, it might be a good option for the twister type 100 kilowatt application, where you don't need that C rate that's gonna be very demanding. That could be yeah, really, really quite useful.
We're using a company called Bollore in France. It's maybe worth having a look on their website.
Yeah, no, I think I've seen their stuff before, but yeah, it sounds, yeah, there's good stuff out there, but yeah, it's just a pack level, just running the numbers and seeing if it works.
Cool.
I don't think you said, if you did say, I missed it, I don't think you said what the speed that you need to get to is for the speed record.
I didn't miss it. I just didn't want to commit. So yeah, it's hard to tell. So it's going to be more than 300 miles an hour over the 3-kilometer record.
Right.
We don't quite know where we're going to be yet. We're pretty close to being able to do the simulation. So we've got a few more performance, sort of straight and level performance runs to do before we put the numbers in the simulation tool. I think it'll be a bit more than 300, but it's going to be a balance. Actually, I think one thing we're going to have to see is, so remember the 3-kilometer record is 4 runs over a 3-kilometer track, which means you've got quite a lot of turning to do. And obviously the time that you're turning, you're not actually being recorded for speed, and you're burning energy. Traditionally, when the guys go and set these amazing records out in the States up at 7,000 feet density altitude, they literally go off miles and miles and do a really gentle turn, wind the speed up and come hooning in. Ours is going to look a bit more like a Red Bull Air race. So we're going to be off the end of the 3 kilometers and then turning efficiently as possible to try and get back into the timed bit. and obviously we're gonna lose a fair bit of speed in the turn. So we'll find about. We actually think the 15-kilometer record, where you've only got to do 2 runs, you've basically got to do an out and a back. We might actually be able to go faster because we won't need to manage the energy as much.
Yeah.
So we'll see.
Cool.
But I think we've done. I think we've been 260, 270 knots just test flying at the moment. So it's a fast aeroplane. It's such a slippery. I mean, anyone that's seen the airframe, it looks super fast, just sat still. So we've got the right airframe for the job.
Quick question: for your Edge project, which is more limiting, the CG range of the aircraft or the maximum aerobatic weight of the aircraft?
Definitely the maximum aerobatic weight is the issue. Basically, I mean, the NXT is quite interesting. So the C of G is where the C of G of the battery is, pretty much, because it's just such a dominating mass element. I mean, we looked at trying to drive the C of G, and you have to put huge weight in the tail to start pulling it back. So as long as you can get the battery somewhere sensible, and obviously the pilot helps. So in an Edge, the pilot is obviously behind the spar and obviously the center. And as long as you can package a lot of that battery up front and around the sort of traditional fuel tank area, it's not too bad. And you benefit a bit because obviously the Lycoming being out front, the motors and inverters are quite a lot lighter. So it tends to naturally balance itself. We haven't had to work too hard with that. Which we're quite lucky. I mean, one of the ways to probably go forwards would be to integrate the batteries into the wing a bit more, which again isn't going to hurt you on C of G, but from a packaging perspective would be beneficial. But then you're in the world of custom wing and a huge amount of money to do that. So yeah, we just need a bit more weight, really, and which is possible. So we all know some of these airplanes are fantastically strong and a bit over-engineered, so that there is a possibility to sort of engineer that to sort of to be a bit heavier. But and remember, the Red Bull Aeros guys have pushed those airframes super hard, so they all used to run quite heavy with. They've all got loads of doing crazy stuff with water cooling, and they've all got the telemetry in the back. So these guys were running quite hard up against that max aerobatic limit, and as most of them will probably attest to, they were pulling pretty big Gs and over Gs and stuff like that. So we think it's a great platform in terms of just sort of overall sort of residual strength. So but maybe in the future a custom sort of beefed up version would be good for an electric aircraft.
Oh, here we go. I managed to unmute. A general question, Sinjin, about the batteries. Obviously, the onus is on recharging them as quickly as possible. Does that degrade the cells quicker, or is it kind of neutral?
It will, yeah, you're right. You've got to be really careful. So that's why I mentioned you'd have to thermally manage them. So you've got to get them nice and cool before you hit them with that fast charge. If you didn't do that, you're just giving away cell life, and unfortunately, that's going to become quite expensive quite quickly, because yeah, once you've degraded them beyond a certain, I mean, you could lose 10% of their energy relatively quickly doing this sort of performance run. So I mean, on the NXT, we actually think we'll only ever get about 3 attempts at full power, like absolutely giving it everything, because every time we do it, we degrade the battery just on the discharge is so aggressive. So we'll get the pilots flying around at lower power settings, and then once they've proven that they can get around the track accurately, we'll give them the full availability. But obviously, for an aerobatic aircraft, you'd look to strike that balance between running it hard and keeping the battery alive for as long as possible.
The other thing, when you were talking about C&G, with those aircraft, or sorry, the aircraft you're working on, have you had to compensate with weight in the back, or it's just been enough to? No,
we haven't. So it was a huge design consideration. So when we designed the aeroplane, we basically in the CAD tool that we use, you have a full mass allocation. So you're basically actively working out the C of G every time you change anything. So because we couldn't leave it down to chance, because, or even just rough calculations, because we're so close to the max takeoff weight, We can't afford to go put 20 kilograms in the tail because we'll go over, and also it's not really fundamentally very good. So we're actually a bit further forward on the CFG than most NXTs fly. It's actually a common problem that they all had. They all had CFGs that were too far back, and they ended up having to put a huge amount of weight in the nose to counteract it. And it's part of that. I don't know if you've seen, obviously the pilot's quite a long way back on that airframe, and the aeroplane was actually designed for a big Continental twin turbo, and it ended up with a Lycoming, which was lighter, and that meant the airplane was never quite right. So our CFG is actually quite far forwards. It doesn't give us any controllability issues. I mean, it's not an aeroplane. You don't free point it on, you wheel it on, so you're never actually close to, you're never going to stall it because the spin characteristics are pretty ugly and the stall's quite ugly. So it's not an aeroplane that you suffer by having. And also, I don't know if you've seen how tiny the tail is. It looks like someone's got a cassette racer tail and bolted it on the wrong aeroplane. It's a super optimized design. It's amazing to see. I mean, hopefully most of you guys should get a chance to see it at some point in the flesh. When we get it in a museum, it'll be a good thing to come and see.
So no fatty pilots.
No, seriously, Phil O'Dell had to lose about 10 kilograms because, as with all things in engineering, unfortunately, as the details add up over time, unfortunately, the weight just slowly creeps up. And we had to sit down about a year ago and said, sorry, Phil, because the problem is Steve Jones is lighter. So he was in this horrible situation that if he wanted to fly the aeroplane, he had to lose weight. Otherwise, Steve was going to get all the glory. So, yeah, he took on the challenge. Yeah.
Great. Thank you.
There is. Anybody else?
Just a quick question, and forgive me, I had to leave for a short time, so forgive me if it's already been covered. But using your knowledge of the rate of progress in this project so far, and projecting it ahead, what's the realistic assessment of how long it will be before we'll actually have one of these aeroplanes, electric airplanes, flying aerobatics, and working on the basis that, excuse me, a current average aerobatic airplane is 100 grand today? What's one of your airplanes going to cost?
Okay, so I could, so the Edge concept, which is this one, we could build that. We could be flying that in a year. If we started today, we'd be flying that in a year. So as I said, the technology is available. Unfortunately, it's going to be quite expensive. So, I mean, to develop that aircraft, it's going to be quite a large number. And that's the challenge. So yes, I think we can go demo aircraft now. The commercial viability, we are looking at decades. I think it's going to be hand on heart, unfortunately, 10 to 15 years minimum, really, before, as I said, it's all about these guys here getting on with it, pioneering, spending all of the investor money, figuring out what works, what doesn't work, and then we'll all benefit from the filter down of that. Because yeah, we can go build this Edge, but it's going to be an expensive thing to operate. You're going to be looking at, it's going to be a big sponsored type of thing. That's not saying it's not worth doing, and then we're going to try our hardest to go and do it and find sponsors. And I think it would be a great airshow aircraft, and it would be great to compete in it and just show what's possible. And then we've all got to be a bit patient and be enthusiastic about bringing it through at a commercial level, because I mean, let's face it, what's a brand new extra NGs? 400,000 euros, a bit more than that. And of that, we know the Lycoming is about, what was it, $40,000 maybe? I don't know, they're probably getting a deal on them. And that ratio is pretty impressive. The fact that the engine, now the problem you've got, and obviously Extra do a great job, and I'm sure there's some profit margin on that, but it's probably not as good as in other industries. So if you start then adding on 150,000 euro powertrain, you're into some pretty big money. You're into a different category of affordability is the challenge. So it's all about working down from that. I mean, yeah, that's the problem that we have. It is going to be about, it's going to take a while to filter down. And I mean, there's also the element of, well, a Pitts hasn't always been as cheap as a Pitts is. A Pitts at one point was the absolute latest, greatest, hot ship, expensive machine, and it's only over time that it's kind of worked its way down, and I think we'll see a bit of that as we go.
Thank you.
So yeah, so sorry for not better news. I think yes, feel a bit bad, but yeah.
Sinjin, Nick, given that the propellers that you're using look to be the sort of thing that's been developed for Lycomings and Continentals with their very old-fashioned slow rotation speeds, if you had a fresh sheet of paper, would you go for a completely different sort of propeller? Would that make an advantage?
So if anything, so it's about, you can actually spin slower. It's all about spinning slower. So you can turn a bigger prop at lower RPM more efficiently, and it's better for the motor. So the motor is a bit more, so direct drive motors are a bit more efficient at high torque, lower RPM. So actually on the NXT, we run the prop at 2,400 RPM max, which gives you some benefits, because when we're marching along at 300 plus miles an hour, our tip speeds are going to be reasonable. So we get a bit of extra prop efficiency there. There's actually a bit of a challenge around, so electrically actuated props are nowhere near as dynamic as oil governor driven props. So we actually were doing some formation flying with the NXT the other day, and as you know, formation flying is when you're the most dynamic on the throttle inputs, and it was the first time that the actual governing system couldn't keep up. So you physically got an electric motor winding the pitch control unit, and we actually for the first time oversped. Now we oversped to 2,600 RPM, which we know isn't a problem because it's a standard MTV9 hub, so it's all good up to 3,000 RPM effectively. But that's also a challenging area, is the electrically actuated element is going to be pretty rubbish for aerobatics, where you're being quite aggressive with the application. It would be manageable, of course, but you wouldn't be able to just slam the throttle and forget. You'd have to think about it a bit more. Any other questions?
I think at that point, let's wrap up then.
Yeah.
I'd just like to say thank you. I was as a nerd, it was absolutely fantastic.
Yeah.
Really
hopefully it wasn't too tech heavy, guys, but I wanted to give you guys just a reasonable stab at the background of it. And yeah, let's see what happens. Obviously the Edge, we can go do that. We're keen to do that, and it would be fantastic to see that happen in the UK and compete at UK competition. That would be an amazing achievement. So we're going to try our best to make it happen, but as, we just need to find some money to do it and some backing, and we'll be away. So yeah.